video is for section 7, section 4.7 on complete zeros and the fundamental theorem of algebra. Um, First thing is to recognize there is on, I'm going to let you exclude number 26. Number 26 is a pretty involved problem. Um, we've talked about some similar exercises, so there's nothing on the test like it, so you should be good. But the first thing involving, we've talked about complex numbers, numbers that are in the a plus bi form. Um, Now, with regard to those numbers can represent solutions to a polynomial function. Okay, so what we want to do is we want to talk about what do those numbers look like when we're solving polynomials, and put those in with the other solutions that we were already working with in section 6, where we were dealing with the real number solution. So I'll show you a little bit of what those are going to look like here when we get to the problem. So the first thing, though, is that when you're looking at complex numbers as solutions to an equation, okay, complex numbers always come in pairs. Let's put it this way, complex solutions. They always come in pairs, okay? So and the pairs have to be special in that they are called complex conjugates of each other. Okay, complex conjugates. Now, that means that if you have 1 plus 2i, if we know that that represents a solution to a polynomial function, then that means that another function or another solution must be 1 minus 2i, which is its conjugate. Now notice that the I term changed to its opposite sign, but the 1 did not. That's how you create a conjugate, okay? Is you change the sign on the imaginary term, okay, but not on the real term in that complex number, okay? So there is a complex number in standard form and its conjugate. If one is a solution, the other one also must be. Now, what if there is no real component? What if we just have an imaginary? That can happen. So if you know that I is a solution, then that means that negative I must also be a solution. Okay? All complex numbers as solutions come in pairs. Okay? Which takes us also to the fundamental theorem of algebra. The fundamental theorem of algebra says that the number of solutions to any polynomial equation must equal its degree. So number of solutions equals the degree. Now, remember we just stated, though, is those solutions might be real and might be complex, and if they're complex, we know they have to come in pairs. Okay, so let's say, take for example, we know that we have a polynomial of degree 3, or excuse me, let's go degree 5. Okay, if we know that a function has degree 5, okay, then think about with the following combinations. I could have 1 real and 2 pairs of complex conjugates. Okay, 2 pairs means 4. 1 plus 4, there's 5 solutions, or I could have 3 real and 1 pair, or I could have 5 real. Okay? So those are the different ways, depending upon what numbers the function has in it. Those are the different things that could happen. So if you're given a list of possible zeros and it says find the missing ones, all you're doing is adding in the values that are conjugates to the complex numbers that are given. Okay, so that's where they're going to start off. 24 and 25. Okay, number 25 says I have a polynomial of degree 6. Okay, and I have the following zeros. I have I, 3 minus 2I, and negative 2 plus I. Okay, they've given us 3 of them. Okay, all of them are complex. None of them have illustrated their conjugates. So when it says find the remaining zeros, all I've got to do is underneath, I'm going to just mention the conjugates of each. So if these 3 are given, then my missing zeros are negative I, 3 plus 2I, and negative 2 minus I. Okay, so there's the first part of it. Okay, now again, we're skipping number 26. On the back side then, they're asking us to find zeros or solutions to some different polynomials, and from them we want to and just we're going to have a combination of real and imaginary. So let me give you a couple to show you what's in store. There's 2 where you have to use number 28 and 29. You have to use your possible rational zeros list and then use synthetic division from there. But they're both cubic equations, so you don't have to do that once before you break it down from there. So let's do number 29. On number 29, I'm being asked to, so I've got f of x equals x to the third minus 8x squared plus 25x minus 26. Okay, now I want to start by doing my list of possible rational zeros. So you take the last number 26 and you break it up into its factors. You got 26 over 1, which is your lead coefficient here. So that's good. I've got no fractions to worry about. And the same thing is going to be true on 28. So that's going to be plus or minus 1, plus or minus 2, plus or minus 13, plus or minus 26. Those are my only factors of 26. Okay. Now what I want to do is I want to use synthetic division. Okay, because this is odd, meaning degree 3, we know there has to be one real solution. Okay, and that one real solution has to come from this list. It has to. Okay, so what I want to do is I want to find that one, and then I can use quadratic formula to break it down from there. So I'm going to test the number 2, and I'm going to put in synthetic or inside the box here, and let's see if that works out. So bring down the 1, and then multiply. Add the here you get negative 6, and then multiply. Add you get 13, and multiply, and you get 0. Okay, so it looks like my remainder is 0. That's perfect. That's what I need. Okay, my real solution of the 3 is 2. I need to find the 2 remaining. So what I'm going to do, if I put my x's back in, this is the quadratic that's left over after I divide. Put that into the quadratic formula, then x equals the opposite of -6 plus or minus the square root of -6 squared minus 4 times 1 times 13. And that's all over 2 times 1. So 6 plus or minus square root of 36 minus 52 is 16. So this is going to be -16. So that's a perfect square. I can get 6 plus or minus 4i all over 2. And then since 2 goes into both of those, I get 3 plus or minus 2i. So bring the 2 down, and there are your 3 solutions. 2 of them are complex, and they're conjugates, and here's the other one, the 2 is left over. Okay, 28 will work very, very much like that one. You got 1 real and 2 complex conjugates to get your 3 solutions. Okay, but that's a good problem. Again, I think there's even one test question similar to that as well. But that's one way that we can find complex zeros for any polynomial solutions. It's going through that process. Okay. The other ones are factorable forms that you can do in a different manner. For example, number 30. Well, let's do 27, because I want to remind you about that one, and then we'll 31, and then I think that'll help you. 27 is the difference of squares. Okay, so I'm literally going to take this f of x and change it to a 0. Okay, excuse me, this is x to the 4th. Okay, it's still perfect squares, so when I set it equal to 0, this thing becomes x squared plus 1 and x squared minus 1. Now, that means that x squared plus 1 equals 0 and x squared minus 1 equals 0. If you go, there's 2 ways you can go. You can factor again, this is difference of squares over here, or just use the square root method. You get x squared equals -1, x squared equals +1. When I square root both sides here, okay, don't forget the plus or minus out in front, square root here. Remember, the square root of -1 is just I. So x equals plus or minus I. There's 2 answers. Here, the square root of 1 is 1, so x equals plus or minus 1. The degree up here says I should get 4 solutions, and here they are. 2 real, 2 complex. Okay, so that's kind of a special form to deal with. 30 and 31 are both also a special form. They're like quadratics. They're called quadratic in form. On number 31, you know that f of x equals x to the 4th plus 5x squared plus 4 Okay, again, set it equal to 0. Okay, what are the factors of 4? Since this is a fourth power and this is squared, I can take this trinomial and just unfoil it. The factors of 4 that add to 5 are 4 and 1. So I took the x to the fourth power and broke it up into 2x squareds. And then I took the 4 and the 1 and broke it up so I know I can get 5. If you set each one of those now equal to 0, now we can do like we did on that previous problem, use the square root method. This means that x squared equals negative 4 when you subtract the 4 over. X squared equals negative 1. Square root both sides again. And make sure you do the plus or minus so you don't lose part of your solutions here. Negative 4 becomes, this becomes plus or minus 2i. And just like we set up above, the square root of negative 1 is plus or minus I. So you will be able to factor number 30 like that one as well. And those are a little bit easier kinds of problems. If you recognize that they're a special form, it doesn't require all the trial and error that you have to do with the PRZ and the synthetic division like 28 and 29. Okay, but I do believe the test has like 2 questions of that same type. So you know, use this to help you out with those as well. Okay. Thank you.